Good morning to all our attendees and a warm welcome to those joining us. We are thrilled to have you all with us today for our webinar on I3C Protocol Validation, Traffic Generation and Electrical Validation. My name is Pranav Jagdish and I'll be host for today's session. We have two esteemed presenters here with us today, Godfrey Coelho and Brijesh Chandrala. Godfrey has over 25 years of experience in the test and measurement industry, and Brijesh is a seasoned technical lead with a wealth of knowledge and experience in designing and validating high-speed protocols. During the webinar, our presenters will share their knowledge and experience on I3C protocol validation, traffic generation, and electrical validation. We encourage you to participate actively in the webinar by posting questions on the Q&A window. And we have devoted the last 15 minutes of the webinar to address these questions. Please note that the webinar will be recorded and a link to the recording will be sent to you after the session. So if you experience any connectivity issues during the webinar, don't worry, you will not miss out on any valuable information. Now, without further ado, I would like to hand over to our first presenter, Godfrey. Godfrey, over to you.
Good afternoon and good evening to all of you. Thank you for joining this session. So today's agenda for the webinar is a little bit about Prodigy Technovation, because some of you, the Prodigy Technovation is new to you and just wanted to know how long we have been in business. And Brijesh will take you over to the overview of I3C interface and the conforming test cases. And then I will talk about some of the use cases about I3C debugging, like how testing and how to test people use that. Because Prodigy Technovation has been involved with the I3C interface since the inception. Like way back in 2017, when MIPI Alliance conducted the first Plugfest or interoperability test in Atlanta in US, we were part of this activity, and we have been very actively pursuing this technology and listening to our customers and providing the updates on a regular interval. So based on this experience, we are going to share different use cases of validation in the different use cases. And then we followed by the demonstration of I3C controller and target validation, traffic generation, and also electrical validation. So all those products, you will be able to see a very live demo so that it can be very effective for you, how it can be used in your use case application. So Prodigy Technovation is headquartered in Bangalore in India. We have been in business since 2009. We are now almost completing 14 years. We can say we are a 14-year young company and entering into a teenage kind of situation for us. And we have been having a distribution channel in Japan, Korea, Taiwan, China, Germany, France, Italy, and Israel. And you want to know their contact details, please visit our website where you can find all the details of our distributors. And we started with developing application softwares for Tektronix oscilloscope way back in 2009. And we developed different applications which runs inside Tektronix scopes like I2C electrical validation, SPI, eMMC, SD, and SDIO, and so forth. And during this engagement with the customer, many of them told us that they were interested in a hardware-based protocol analyzer. And we started this activity in way back in 2015. Our first product was eMMC SD UHS1 SDIO protocol analyzer. And thereafter, we have still a range of products now. So we have a UHS2, UFS, Universal Flash Storage 3.1 and 4.0. 100 base T1 automotive Ethernet, and then many I3C, like many low-speed serial interfaces, such as I3C, RFFE, I2C, SMBus, QSPI, JTAG, MDIO. We have an exerciser as well as protocol analyzer. And then we recently, a year back, we launched a 16-channel logic analyzer, which is having a highest real timing analysis at 1 gigasamples per second in its class with a different protocol decoding capabilities. It is just not does the protocol decoding, you can also trigger on specific protocol packet content. So currently we are supporting I2C, SPI, I3C, SPMI, CAN, CAN-FD, and QSPI. And today we will be giving a demo of I3C protocol decode and trigger analysis. Then when it comes to the Tektronix oscilloscope, we have provided a range of electrical validation and protocol decode software. Almost we cover protocol decoding for many high-speed and low-speed serial interfaces. And to know more about Prodigy Techno, you can visit our website. So most of the product information, application notes, or if you like to see a demo, you can very easily reach us through our website. So let's look into the current low-speed interfaces used in many of the embedded designs, right? So very commonly used low-speed interface is I2C. So I2C is an inter-IC communication. It basically has a master and slave kind of a topology where highest data rate is 3.4 megabits per second, and many slaves can be connected to the master on this bus. But I never seen any of the applications people are using at full speed at 3.4 megabits. The highest speed what I have seen in the market is around 1 megabits per second. That's mainly due to some of the limitations in I2C bus, in my opinion, the capacity loading and some of the noise it gets generated. So people try to restrict using I2C at 1 megabits per second. The next technology which people widely use in embedded application is a SPI, serial peripheral interface, which is also a master slave kind of a topology, but it has a multiple IOs. Like there are two lines, which is MISO and MOSI. They are for transferring the data between the master and slave. Then there's a chip select and clock. So basically, this topology increases the number of IOs depending on the number of slaves to be connected to the master. So it increases the complexity. And this bus can be used up to 60 megabits per second in some of the use cases. And this is a very second commonly used interface. And apart from I2C and SPI, there is also a UART interface. Now, what MIPI Alliance over a period of time has come up with this I3C interface, which is basically trying to simplify this different topology requirement to a one consolidated interface, which is I3C, right? So improved I2C. It's I3C stands for improved inter-IC communication. The maximum data rate on a single lane, it can go up to 34 megabits per second using different encoding technologies. And more detail about this I3C, my colleague Brijesh will be talking about it.
Thank you, Godfrey, for introduction. So, okay, so why I3C came, right? Because I2C, SPI, and all, it is not fully standardized, because SPI works at higher speed, but it is not standardized because based on the company to company, they will use their own SPI protocol. So that is why this I3C interface came into picture. It is like standardized bus, all the transaction, everything is like standardized, and it can go up to 12.5 megahertz. So it has multiple modes actually. One is SDR, single data rate, TDR is double data rate, and it has other features like in I2C we required extra pin to generate the interrupt. But in I3C, it is included in the SDA bus itself. There is a mechanism where we can generate IBI, and it has dynamic address assignment feature also in I3C. So if some new device is sitting on the bus and it wants to communicate with the master, so there is one more format is there. It is called port join. So that target can issue the hot join command, hot join, and controller will issue the dynamic address assignment. There are multiple ways to assign the dynamic address, and based on the priority, master can decide which slaves to give highest priority. So it will assign the lowest dynamic address to that slave. So whenever IPI in-bed interrupt come on the line, that time controller knows, okay, this is highest priority slave, and it will win the arbitration. So that slave can continue sending IPA on the bus, and master can clear that interrupt by doing based on what is a handshake between controller and the target. Good. Good. Next slide. Yes, and these are the applications for I3C. It is used in initially when this I3C started. At that time, it was mainly for sensor devices actually, but nowadays it is more to other applications actually. So now it can be used for power management IC, IoT, automotive also it is useful, and in consumable electronics and embedded devices. So it is like I3C can be used in all the applications. Okay, so there are two specs. Uh, you- One is basic specification and mute yourself. Uh, One is basic specification and one is full specification. Okay, basic specification is available for public. Okay, and full specification is only available for the MIPI members actually. So there are some features are not available in basic specification. It is like timing control and ternary encoding. Actually, ternary encoding is encoding where uh, uh, it can increase the speed actually. DDR is up to 25 Mbps, and with ternary encoding, we can send 3-bit information in two transactions actually. So it can go up to 33 megahertz actually, Mbps. And after that, whatever supported features are, it can do read write, CCC, DDR, BT, and set ASI is another command where controller can assign the dynamic address to the slave actually. And for further information, you can go to MIPI website. It will give the differences and spec. Next. Yeah, so it is like I3C, data speed and data modes. So this supports legacy I2C devices only for 7-bit. It will not support for 10-bit addressing. Okay, so single data rate, it has three parts. One is private read-write operation will happen in SDR. Then it can send directed addressing, which is like, let's say one controller and three targets are sitting on the bus. So it can send to particular slave with directed addressing. After that, it has broadcast. So whenever it is broadcast, at a command is sent, it will receive by all the targets. Then we have multiple data rate, as I mentioned, DDR. It is like double data rate. After that, ternary symbol for legacy mode. It is like whenever one I2C slave target is present on the bus, that time this mode is used. So it has some mechanism that that clock cannot be seen by I2C slave. Okay, so because it will have 50 nanosecond spike filter. Okay, so whenever controller moves into this mode, then I2C device will not see the clock, so it will not disturb the I3C bus. After that, ternary symbol for pure bus. So whenever in the network, controller and all the targets are I3C targets, then a controller can use this mode. But till now, we have not seen adoption for these modes, actually, ternary modes. Next. Yeah, so a protocol has multiple functions like bus communication, bus precondition, after that hot join, uh, uh, and priority level. Means I have covered these things in my previous thing. It is like priority, how to give priority and invent interrupt. After that, there is a new function is that peer-to-peer communication, and CCC is nothing but command code. So everything is structured. So it is easy to adopt by new companies also, new adopter. So once standard is fixed, it is interoperability will be easy. And in HDR mode, there is another terminologies like HDR exit, HDR. There are some commands. When we issue that command, it will move to HDR mode. Okay, HDR has three mode: DDR, TSP, and TSL. So these are the terminologies for that. Next. Okay, so conformance test suite. Okay, so for 1.1.1 I3C main spec as well as basic spec, there is one CTS. Okay, so that CTS is defined to improve the interoperability of product. Okay, actually, MIPI is not giving any approval or certified that it is like once this CTS is working, it means it will work in all the condition. It is not like USB and PCI, because for that some certification can be given, but for this I3C there is certification is not there. So this is just to give confidence. Okay, once all the CTS are working, it means our device will work with most of the controller or most of the targets. So this is give a reasonable level of confidence actually to it will work in many environments. Next. So current CTS has STR capabilities and some error recovery method, detection method, and HDR tolerance or repeated start or exit condition. But it is currently DDR mode capabilities are not listed in the CTS, but it is live document. Working group is working on this, and whenever this other modes CTS is ready, it will be included in the CTS document. Godfrey, would you like to take it from here?
Thank you, Brijesh. Yeah, so let's look at the deployment of this I3C technology. So it's normal that initially we start with developing the I3C IP. So once we develop the I3C IP, maybe we'd like to prototype that on a FPGA platform. And that's where you need, if suppose someone is developing a controller IP, in that case, they need a kind of a simulator or emulator which they can connect and they can test it with the target IP. So you need some sort of a testing tool at the I3C IP development phase. And the next phase is integrating this IP on a SOC controller or actually a sensor device or no or a DDR or a PMIC kind of application. That's when you try to make a complete development where you try to do, the people try to do a emulation and prototyping, and that's where we do a pre-silicon validation. And once we do a pre-silicon validation, everything is done. There is other IC design activities like the backend activity, like routing the signals, all IC design activities, and the GDS2 will be released. And once that is released, IC will be fabricated. Once the wafer comes back, it will be packaged, right? Once it is packaged, so there is a need to do a post-silicon validation by sending different traffics of I3C, like changing the amplitudes, changing the setup and hold time of the signals, doing error injections, all kinds of post-silicon validation needs to be carried out in the protocol layer. Similarly, there is a need for electrical validation. making sure that all the rise time, fall time, setup time, hold time, there are different electrical timing parameters. They need to comply with the electrical spec of the I3C. So by ensuring this kind of testing, so that we can make sure that most of the time the product, the controller, and the target very easily and comfortably interoperate in an embedded system or any other application. Once the chips are available, when the integrated circuits are available, they need to be given to different customers. That's when the application engineering comes into picture, where we will try to make a different products or evaluation boards or sample designs for different applications. And that's the time. Sometimes you may have a target or a controller, and in order to showcase your product capability, you may need to have a emulation of a controller or target. In that, you also need a simple exerciser. And designers who are designing systems, right, using the controllers and the targets, and they need to, when they make the boards, and the software needs to be integrated with the board, and they need to debug the communication between the controller and target. And that's when we need to have a system level debugging tools. So this is how a technology which moves from the IP development phase to all the way down to the system level designs. And there will be also field feedbacks like the field returns and so forth, which is very similar to, again, application engineering. This forms a complete cycle of a complete product development and deployment in the for a given technology. Now let's look at what it takes to do a IP development and how we can debug those testing requirements. So the key requirement in IP development is we need to generate I3C traffic at different data rates. Like when there's a new IP is being developed, if we are developing a controller, then we need to have some sort of a target simulator or emulator which can provide the real world signals and traffic to the developed IP. And as per I3C specifications. And also there is a need to do the in-band interrupt test. It has to support all the features as per I3C specifications. At the same time, the I3C like controller, if you are developing, it has to support the legacy I2C devices, whether it can accommodate such a application. And we should be able to do some error injection to the IP, so that we can know that whether the product is robust enough to withstand all the different test scenarios. And also we need to emulate a I3C network, because when the very new technology comes into the marketplace, so we do not have many devices in the market. So there are some sort of a different product is required which can emulate a small I3C network. Like someone is developing a target, then the test equipment should support a controller with a couple of slaves so that they can form a small network and exchange traffic between the different devices and make sure that the product is very stable and robust. This is where Prodigy developed PGY I3C EXPD comes into picture. We have a very stable product. It's been in the market for last 4 years now. It supports and meets all these requirements. So one can use it to generate different traffic, error injection. It also supports I2C devices, high BI, and also can emulate a I3C network. This is the first phase of the IP development. Once the IP is developed, like the IP needs to be integrated with a system on chip, SOC, right? Or the target devices. When we do that, the entire SOC as a development process in the pre-silicon domain or the front-end part of the design, right? It goes through the verification. And the next part of the verification is emulation and prototyping, where users like to provide a real-world signal to the prototype and see how does the entire SOC is performing. So one of the challenge in SOC emulation and prototyping is that, so the designs are very large. Like the SOC can be millions of gate. Today it may be hundreds of millions of gate design, which needs to be ported onto an FPGA platform. And normally these designs will not be accommodated on a single FPGA. So you need multiple FPGAs to do the prototyping of an SOC. And all these FPGAs are interconnected. and they communicate each other in order when we do the partitioning and prototyping of the design. One of the challenge happens is that even though the SOCs operate in a real world very high speed, during the emulation and prototyping, they normally work at a very, very low speed. But it is still much better than the simulation and verification environment. So in order to support such a requirement, there is a test equipment requirement which needs to accommodate such a low speed performance and still provide the protocol data. Like for example, in the case of I3C, the lowest data rate as per I3C specification is 100 kilohertz per second. But the prototyping solution on a SOC platform or an emulation environment may not work at 100 kilohertz. It will go down to maybe sometimes 1 hertz data rate. So the test equipment needs to provide that kind of a capability. And that's where Prodigy's I3C EXPD has a capability to generate a I3C traffic at 1 hertz. So it can start from 1 hertz. You can vary that, like 1 hertz, 10 hertz, 100 hertz. Depending on your requirement, you can specify what data rate you want to generate, and you can test with your SOC platform. And this is very ideally suited for an emulation and prototyping environment. So our users can start using our product from the very beginning of the design, like when they think of developing IP, all the way up to the deployment. We will see that in the next slides. The next phase of the testing and validation is a post-silicon validation. So as I mentioned, once we have the wafer from the foundry, this needs to be packaged. And once it is packaged, there is a need to make sure that all the packaged device is completely compliant to the I3C specifications. So in order to test that, again, there are a lot of different protocol tests to be run. As Brijesh mentioned, we also need to run the conformance test cases also. Plus, many users, they write their own test case. The test equipment needs to be flexible and should have a API support for automation so that these activities are like a repetitive kind of nature as and when next version of the SOC is coming up in the market, right? So it should also support the APIs. So we need a device which can vary the amplitude of the signal. Suppose in SOC, IO is supporting a voltage from 1.2 volts all the way to 3.3. So our test equipment should have a support for varying the amplitude. Similarly, timing variation. There are setup and hold time variations, duty cycle variations, packet to packet, inter-message message timing variations. So there are different timing parameters are involved in a protocol. And all those timing parameters should be flexible to change, but the test equipment should support that. Along with that, it should support error injection, emulate a small I3C network, like if you are doing SOC controller, testing SOC controller. In that case, the test equipment should have a capability to do some kind of a slaves network, and we support 3 slaves in our EXPD product. And also we can configure one secondary master, so that will enable the complete emulation of the I3C network. So PGY I3C EXPD can support with all these requirements. Okay. And then it's just not the protocol level testing is the requirement in a post-silicon environment. User also needs to make sure that I3C bus, the clock and data, the electrical timing parameters also within the specifications. And Prodigy, we offer a PGY I3C electrical validation software, which runs inside Tektronix oscilloscope. We also support the new generation oscilloscope like MSO5B and 6B, and also the volt scope platforms like MSO 5000B or DPO 70000B. Or in case if you're having other vendors oscilloscope, you can always approach us, and now we can try to support your requirements and other vendor oscilloscopes too in an offline mode. And then we can run the test. We can automatically get all the timing parameters and compare it with the limits which are specified by the I3C standards document. And then we can say pass or fail. And if the test is failed, you will be very keen to know how to debug that. And we have a lot of debugging capabilities built within the software. where you can see all your electrical timing parameters, and then you'll be able to know where exactly it is failed, and you can directly link to the waveform location and able to pinpoint, okay, this is where exactly the waveform shape is not all right or something is going wrong. This could be due to the reflection in the bus, or this could be some change in the impedance or the pad issues and so forth. So there are variety of debugging tools are available within the electrical validation tool. So the next, now we have the post-silicon testing is done. The next phase of the product is normally deploying into the marketplace, and we make different evaluation boards debug to showcase how the I3C technology can be used for different purposes. So in that scenario, like for example, you have a I3C SOC controller, and where we want to show people how to connect to different slaves and emulate different slaves. So Prodigy, we offer something called I3C EXPD, the light version. And this light version can generate the traffic at the full data rate, like the 100 kilohertz to all the way up to 12.5 megahertz, with a fixed voltage of 1.8 or 3.3 or 1.2 volts. You cannot vary the voltage, and you also cannot vary the timing parameters significantly. And you'll be able to emulate any of those slaves or a master and showcase your actual application to your end customer, how you can meet their requirements. So it is basically builds a lot of confidence with the customers, how they can use it. Now, sometimes application engineers, when they go to the customer, there is a need to debug their system also to make sure that everything is working fine. And between the master and slave, the traffic is all right. Now, in such cases, you need a much simpler product. So we have a 16-channel logic analyzer with 1 gigasamples per second timing analysis capability with a built-in I3C trigger and protocol decode capabilities. So with this, you can probe the communication between a SOC controller and a target, and you can exactly know what exactly being communicated and whether there are errors and so forth. And the logic analyzer can be capable of decoding those packets and showing the entire traffic. So we have again a sophisticated tool which will take care of that. Now, there are some scenarios which we have come across. So, which is basically like much more complex use cases of I3C, where there is a host controller and then there is a hub. And the host controller will communicate with the multiple hubs, and each hub will have its own I3C network. Now, in this scenario, to debug the use case, you may need a tool which it will monitor the communication between the host controller and the hub. At the same time, it is also monitoring the I3C traffic at each of the hub. So it's basically what I shown you in this slide. We have around 8 to 9 I3C buses to be monitored, okay, and simultaneously see what traffic is going on each of these I3C bus. And this becomes a little complicated use case. But Prodigy as a logic analyzer, which is a 16 channel, with that we can monitor 8 I3C buses at the same time. So we can probe between the host and the hub. Similarly, we can also probe each of the I3C bus, and we can simultaneously monitor all the I3C traffic going on this application. So which is a very powerful, like one of the hub is getting switched off, or some error packets are being generated, and it's very complex and very difficult to monitor the protocol issues. And that's where this product PGY LA Embed with a multi-channel I3C protocol decode capability would be very, very useful. So that's the different application. Now I'll switch, we will switch to demo. I will request Mr. Brijesh to continue with the I3C exerciser and protocol analyzer.
Thank you, Godfrey, for giving such a good introduction, means application where it can be used, all this. So let's switch it to demo. I'll give demo very quickly, and our technical team will share the links in the chat box also, means our previous demos. Okay, so this is how our UI will look like. Okay, so here we can configure our I3C EXPD as master, secondary master, and three I3C slave and three I2C slave. It is like combination of secondary master, I3C slave, and I2C slave. You can add three devices actually, and one master. You can configure as internal to our EXPD or external. We have 2.2 kilo ohm pull-up register. We can enable or disable. And this device supports 1 volt to 3.3 volt in a step of 30 millisecond. Okay, you can vary the voltage. For lower voltage, we have resolution of 10 millivolt, but at the higher voltages like more than 2.5 to 3.3 volt, we have 30 millivolt resolution. So this can be used for automotive kind of application where voltage is key. And then we can set the trigger out and trigger in. So I will add one master and one I3C slave. So in slave, we can configure this BCR, TCR registers. So in DCR, we are supporting two kind of slave. One is generic slave. It is behave like a FIFO. And one is memory slave where you have to give address and it will be stored into that location and you can read it back. After that, these things we have taken from MIPI website because whoever is registered contributor member or MIPI members, they will get the manufacturer ID actually. So you can configure this manufacturer ID, okay, and just close this and add the device. Okay, so we have I3C bus network. Whatever devices if you add, it can be shown here. And this network also can be saved and you can recall this network. And mode is currently EXPD, so I will send some transactions. Okay, so we have some preloaded script where I will just send enter DA command. Okay, so here we have, as Godfrey mentioned, we can vary all the parameters in whatever mentioned in the I3C spec. So CSOD means open drain frequency, we can vary T high, T low, then T-cast value. This everything can be varied in step of 10 nanosecond. After that, here this is push-pull frequency. So in EXPD, we can go from 1 hertz to 12.5 megahertz, and that also in step of 10 nanosecond. And this is TCO, clock to queue delay. So here we have resolution of 18 picosecond. Okay, so that way you have very good control over the bus, and you can test your setup and hold time. After that, this is like extended, so where we can change this parameter TSU and STA and TSU at stop. Okay, so I'll just send this command. Okay, so it has sent the command 7 enter DA command, and slave has responded with PID, BCR, DCR value, and our master has assigned dynamic address 8. Okay, I will just send some private message. Okay, so here if you see TCO is 10, so in right operation, if you see in our plot view, it is 8 nanosecond. Okay, because our plot view works, plot view resolution is 4 nanosecond. Okay, so we can see in step of 4 nanosecond, and it is like if you send immediately, our software will start decoding actually. Means user don't have to wait for the decoding, and we have some loop counts. So same thing will be run at 4 times actually. Private write message. Okay, so here it has run 4 times, and we have search and search, advanced search, and in report we can save this report in PDF or CSV format, and we can see the analytics. So we can put the timestamp also actually. So if there is any errors, we can show the error counts. We currently we have sent enter DA one time, so it is broadcast command. So it is showing one, and after that I did some read write transaction. So total 20 transaction has happened, and data is transferred like 104. And if we change the dynamic address, then it will reflect here. Okay. Okay. So here cursors we can put overlaying bit. We can save the snapshot and put it in the report. So it is like full feature packed plot view. And here in the selected view, wherever if you click on decoded result, so appropriate frame view is updated here, and it shows the frequency for that byte. Now I will just quickly go through the CTS. So whenever user wants to run CTS, they can insert give this information, DUT version, serial number, and all. I'll just click on stop. Actually, currently we have already have one slave and one master on the bus. So I will just say configuration is done. Okay. So now we have slave test cases. Okay. So DUT is slave. Okay. We support both the test cases in CTS. We can make it DUT as master. Then our I3C EXPD will become slave. And if we have selected as a slave, then our master, our I3C EXPD will become master. So for all the test case, we can because some targets may not support all the addressing mode. So we have given option because some of the test case we have to assign the address. So we have given option assign dynamic address with enter DA or set ASA or set DASA. So based on this selection, uh, after that we have system configuration where we can give the scaling factor actually directly. So whatever parameters are inserted here, whatever is given here, it will take the factor of that. Okay. And whenever we want to run this CTS, we can configure the these are the same parameter. Sys is for push pull frequency, sys OD is for open range, and extended is for repeated start and stop condition. So slave test cases, we have listed all the test cases. So here you can select all also. Okay. Or you can select individual test case, and if you just click on run, I'll just start the acquisition, and if you just click on send, so it will send CTS test case one by one, and you can see here, and once it processing is done, it will give count like pass or fail, and if it is failed, then it will indicate where it is failed. So we are strictly referring the CTS document. So this test case got passed. Okay. Then immediately it will send the next test case. So to run all total test case, we required I think 10 to 12 minutes to run the all the slave test cases. So it is very handy, and it is configurable that whichever test case you want to run, you can just select that and you can click on send. So automatically it will handle this uh, test case. Then you can directly go to report and you can export in PDF. I'll just give test 1, 2, 3. So it says report is generated. See, my report is open. Okay, so here whatever initially it will ask for this information, right? So that information will come here with the date and time. And whatever configuration we have done, that will shown here. Okay, and we have run 2 test cases. Okay, and both are passed. So it will write this test case is passed, and it will give protocol list also, means at what frequency and what thing we have done. So this will contain a report will contain this information. If we have selected the snapshot images we want to insert, then during that configuration we can select that, and whatever images if we have taken there, then in the report it will append in the last. So yeah, I think I have covered very quickly, but I have covered most of the features. I request Godfrey to take over from here for
Yeah, thank you, Vijay. Okay, let me now give a demo of our oscilloscope electrical validation software. Okay, let me figure out where it is. Okay, let me share my screen again. So yeah, so this is an oscilloscope. We are using currently MSO 5 and 6 series oscilloscope. We have captured a series of softwares using Tektronix oscilloscope. They are currently loaded on the ref channel. Okay, and let me load the software. Software. Let me minimize this and launch the software. Okay, yeah, you can see the software now. Let's go back and get the scope screen back. And okay, I have software here. Yeah, so this is the software which is the I3C electrical validation and protocol decode. It supports, so it also does the decoding of the waveform captured by the oscilloscope, and also does the electrical validation. And but software needs separate licenses depending on your requirement. You can choose to buy one of them or choose to buy both of them. These are the different electrical parameters for open drain, and these are the different parameters for push-pull applications. And if you're running, I think I2C, you can also do fast-plus electrical validation test for I2C. Now, coming to the waveforms, we are now running this test case from the scope waveform, oscilloscope directly. But if you have a saved waveforms in WFM format, you can recall them and you can load it. Or if you have a waveforms from in a H5 file format, then you can also use it. Once you configure it, you can also see the limits here. All these limits are as per I3C specification. But in case if you want to edit and modify them, so you are free to do so, and you can also save them and then recall them later. And then we can also do some triggering, but this is for protocol level triggering in oscilloscope. But in order to use this feature, the oscilloscope should support the serial pattern trigger. For example, DPO 7000 or DPO 70000 series oscilloscope, where you can use this capability to trigger on a particular I3C packet and capture the data. So let me just note, I already configured the waveform. Clock is stored in ref channel 1 and data is on ref channel 2. And I will just click on a single. The software will extract the waveforms and it will analyze the waveform for all the selected electrical parameters and display the results in a minute or two. So we can also generate a report and export this data into different CSV or text file format. You can generate report in a PDF file format. And when you're generating report, you can also have different images. Now here you can see my measurements for open drain and push pull. So what all different measurements are available. You can choose them. These are the measurement, like what is the minimum value, what is the maximum value, and the mean value. So there are 176 instances of T-low open drain condition in the acquired waveform. All those are different. All the events are measured and the mean has been taken. And also we will show you the min and max value. So all these parameters measured at instance of time and displayed. If it shows NA, it basically indicates that this condition is not present in the acquired waveform, hence it is displaying it as a not available. Okay. Now, if you want to look at the push-pull, you can use a push-pull parameter. And if you want to look at the protocol view of these captured waveform, you can select on protocol view. And here we will show you all the protocol parameters, decoded packets. Okay, you can do a search and filter and so forth. Everything is possible. In case you want to look at the detailed view, like suppose you have a protocol decoded packet as well as a waveform, you can select a packet and you can view them. And you can also zoom into a particular area of the waveform. Like for example, this area you can zoom. So you can also fit to screen. So all features you can do it you can do the decoding. In case of an oscilloscope, the decoding is done only for the captured waveform. Normally, oscilloscopes can capture a few milliseconds of data. Because of the architecture, the scopes cannot capture data for a few seconds or a few minutes or sometime maybe for a day. So such a use case is not possible. Now, in order to support such use cases, as I talked about, we have a 16-channel logic analyzer. Let me share that view. Let me stop sharing here and bring up the software, which is a logic analyzer. You can see here on my screen now. I think you can let me share the screen and show you my setup here. So I have a setup here. Can you see logic analyzer setup? Okay. Yeah. So you can see this is our 16-channel logic analyzer. We are having a I3C traffic generator where we are probing using clock and data that's been connected. And this logic analyzer connect a host computer using a USB interface. So let me bring up the software which does that. So now you can see the software. So there is a configuration panel. Let me go back and maybe share the logic analyzer screen. I think now you can view that. Okay, so in the configuration panel, you have a flexibility to view only logic analyzer mode where you can select, you can see all the 16 logic analyzer and you can decode, look at the timing waveforms. And if you, in case you want to do a protocol analysis only, we can select a PM mode. Now, if you are looking at trying to decode I2C SPI UART, this is what you have to select. Now, our interest is looking at I3C traffic. So I have connected clock to channel 1 and data to channel 3. So we can connect any one of the channels. And then I can go and establish connection. So, and then I will just say acquire traffic. So the logic analyzer will start capturing the protocol waveform, and it will show you all the protocol packets, decode it simultaneously and display. So right now we are trying to generate the traffic at a full speed at 12.5 megahertz. And this is one of the best part of Prodigy logic analyzer. It has a 1 giga samples per second. With that high sample rate, we are very comfortably able to capture traffic operating at 12.5 megahertz, and we can look at all the packets. And what you can observe here is that we already captured 6 seconds of data. We are continuously streaming this data to a protocol to the host computer hard disk, which will help you to capture the different data for a very long period of time. So this is a very powerful tool for debugging at the system level area. So I think we are almost there in the time. I think we also support already I3C triggering. I will just quickly show you. So you can go here and you can select trigger capture, and you can select which protocol packet you want to trigger. And then you can set the different repeated start address, all the parameters you can do. And so we also support the trigger capabilities. So this is a very quick demo of logic analyzer with I3C trigger and decode capability. Very useful maybe for the application engineering team and the system level designers who can like to monitor the traffic between the host and device. And what Brijesh has shown you, the EXPD, the exerciser and protocol analyzer, which has the flexibility to generate traffic at different speeds, different timing parameters, and different amplitude, and with the error injection, CTS, everything is available on that product. So these are the different tools are available to do the validation of I3C IP, and there are different phases of validation we already talked about. And that's the overall presentation we wanted to do it today. And we are now ready to take any questions. Let me stop my presentation here, this sharing.
Thank you, Brajesh and Godfrey, for the very informative session. So we have a few questions here. Let's start with one. The first question is a two-part question. How to connect the I3C exerciser to the DUT, and what type of connector is required in the DUT to connect?
Okay, that's a good question, because always how do we connect to the DUT is a challenging. We provide a flying lead sets with a female header pin, and we expect the DUT to do a male header pin with around 2 millimeter square, I think. So where we can insert directly and we can probe the I3C signals, as well as when it is an exerciser and analyze exerciser also, you can provide these header pins and we can very easily connect to the DUT. And the flying leads are special cables. They are coax cable, so that they will operate comfortably at the 12.5 megahertz data rate. I hope that answers the question.
Thank you, Godfrey, for that answer. Let's move on to the next question. The next question is, do we need to connect the ground of the DUT to the analyzer?
Yes, we will strongly recommend connect the ground of the analyzer or an exerciser to the DUT. There is a tendency with the users that since it's a 12 megahertz or sometimes even at 100 kilohertz, not to connect the ground because it's a low speed. But normally we strongly recommend, because there could be some timing variations and overshoot and undershoot kind of a scenarios, ground being missing ground. So make sure that ground is always connected. We provide a ground pin next to the data signals, so that there is an immediate return path to the data. So it's a signal integrity is maintained.
Okay, thank you, Godfrey.